Determining if a control system is stable usually requires finding the exact roots of its denominator. But once a polynomial reaches the third degree or higher, especially when it contains an unknown variable, calculating those roots directly becomes incredibly difficult. That is where the Routh-Hurwitz Criterion comes in. It is a mathematical tool that completely bypasses the need to find roots, allowing us to determine stability using only the coefficients of the polynomial. Take a look at this open loop function. It includes an unknown variable gain k. A common mistake is analyzing the open loop denominator directly. To analyze the closed loop system, our first critical step must be transforming this into a characteristic equation. Setting 1 plus the open loop transfer function to 0 integrates the feedback loop. Clearing the fraction pulls k into the string. This polynomial, s cubed plus 4s squared plus s plus k minus 6 equals 0, forms the Routh-Hurwitz baseline. Now we can build the Routh array. We start by setting up an empty grid, listing the powers of s in descending order along the left side, from s cubed down to s0. This table shows how to populate the initial framework using an alternating zigzag pattern. For the s cubed row, we take the first and third coefficients, giving us 1, 1, and 0. For the s squared row, we take the remaining terms, 4 and k minus 6. Executing this alternating setup perfectly is critical. Every calculation that follows relies entirely on the precise geometric positions of these initial numbers. Looking at the left panel, we calculate the B1 term using a reverse determinant. We cross-multiply the rows above, the pivot 4 times 1 minus 1 times k minus 6. Dividing this by the pivot element gives our final expression, 10 minus k over 4. Before we move on, pause the video and try applying this exact same geometric pattern to solve for the final C1 term in the S0 row. Over on the right panel, you see how to calculate C1. Because the right column contains zeros, the cross multiplication produces a 0 in the numerator. This neatly cancels out the B1 terms entirely, leaving us simply with k minus 6. By following this array structure, we have systematically collapsed a complex, difficult-to-solve polynomial into a clean series of simple linear expressions based solely on the variable k. This slide displays the definitive rule of the Routh-Hurwitz criterion. For absolute stability, every single element in the first column of our array must be strictly greater than 0, meaning no sign changes can occur. As the left panel shows, our first two values, 1 and 4, are already positive. Moving to the center panel for the S1 row, we set our B1 expression, 10 minus k divided by 4, to be greater than 0. Solving this inequality reveals our upper limit. K must be strictly less than 10. On the right panel, we evaluate the S0 row condition. We set k minus 6 to be greater than 0, yielding our lower limit. K must be strictly greater than 6. For the overall system to remain stable, both of these conditions must be true simultaneously. This creates a specific bounded operational zone on the number line where the two regions overlap. This blue box displays our final combined range. K must sit between 6 and 10. Operating outside these numbers pushes the system into instability, while setting k exactly at 6 or 10 results in marginal stability, causing continuous oscillations. By applying the Routh-Hurwitz method, we successfully bypassed the complex math of finding exact polynomial roots. Instead, we extracted the exact operational parameters required to keep a physical control system safely balanced.